Ruski Island over the eastern Bosphorus Strait is being built under a federal program of Vladivostok development as a center of international cooperation in the Asia-Pacific region. The new bridge will be a link between Vladivostok mainland and island areas to become an important part of the Primoria region transportation system. The bridge to Ruski Island is of unique dimensions. The bridge, 70 meters high above the water level, and the central span is more than 1,100 meters long. The bridge will break world records. The pylons will be 320 meters high, and the stake cables will be 580 meters long. Bridge construction started in September 2008, and it will be completed by the Asia-Pacific Economic Cooperation Summit to be held in Vladivostok in 2012. The bridge will be built in a record short time, in 43 months. Vladivostok is the largest Pacific port in Russia. This is the reason why the new bridge must let through vessels of any class. The eastern Bosphorus Strait is about 1.5 kilometers wide in the bridge project area. The wind velocity is up to 36 meters per second, and the storm waves are up to 6 meters high. The ice is up to 70 centimeters thick. The temperature in winter drops below 30 degrees minus, and in summer it is as high as up to 37 degrees centigrade above zero. The choice of the bridge design was based on these factors. 2 production facilities were put in place for running efficient construction operations. They are located on the Nazimov Peninsula and on Ruski Island. Each production facility has a rebar welding workshop, building inspection laboratories, mechanical, woodworking, and equipment repair workshops, office buildings, living quarters, and canteens. 4 state-of-the-art concrete mixing plants supplied by Techwil Oy and compactors are operated on the project. More than 1,300 meters of new railway tracks were built to ensure timely delivery of building materials. The existing railway section of over 4.5 kilometers long was upgraded. All building materials are rigorously tested in a special laboratory. Each concrete mixing batch is tested daily for strength, density, water resistance, frost resistance, and water permeability. Special equipment is used to test reinforcement bars for tensile strength. About 320 pieces of special equipment are used in construction of the bridge to Ruski Island. The reverse circulation drilling rigs have been deployed here for the first time in Russia for bridge building. A total of 20 most advanced drilling units have been operated. They include Bauer BG-40, the most powerful drilling rig of its class in the Far East. Up to 280 track-mounted and tower lifting cranes are in operation on the construction site. The Hitachi Sumitomo track-mounted lifting crane can lower rebar cages that are more than 30 meters long vertically into casing pipes. Unique Kroll tower cranes, which can be up to 340 meters tall, are used for erecting the pylons. Construction of the bridge over the eastern Bosphorus Strait started from erection of the viaducts. The viaducts are more than 900 meters long overall. The viaduct piers are from 9 to 30 meters high. Each cast-in-place pier consists of 2 legs. Board pile footings are integrated with cast-in-place grillage. Piles are 5 to 20 meters long. The board piles are of unequal length because of the sound soil that supports the piles occurs at different depths. span is made up of 3 inclined web box steel girders. Nelson flexible studs are used to integrate a cast-in-place reinforced concrete slab with a steel girder. Custom-made machines, which ride on tracks, were installed for concreting the roadway slab. The bridge piers M1 on the Nazima Peninsula and M12 on Ruski Island are the heaviest and most complex structure. They are about 35 meters high. The number 1 and the number 12 are used as the load transfer piers. They take up the horizontal load from the cable-stayed span stiffening girder. Pier bodies are pierced with numerous ducts for accommodation of utility lines and for bridge monitoring system transmitters. The builders used self-compacting concrete for erecting the bridge pier and pylon grillage. They added special components to the concrete mix, which made concrete vibrating unnecessary and cut down concreting time. The self-compacting concrete mix significantly improves the quality of reinforced concrete structure. Man-made peninsulas were rock-filled in the eastern Bosphorus Strait for pylon erection. When construction has been completed, they will protect the pylons against erosion and ice and against vessels' impacts. The pile footing for M7 pylon on Ruski Island was built from the water using a temporary steel eyelet. The man-made peninsula was rock-filled after the board piles and enclosing sheeting had been put in place. Drilling and pile concreting operations were conducted from the water at sea for the first time in bridge building in Russia. 120 board piles, each 2 meters in diameter, have been put in place to build the footing of each pylon. The piles on Ruski Island are permanent metal casing piles. The piles were bored to a depth of up to 77 meters on the Nazima Peninsula. The rock is closer to the ground surface on the island side, so the piles of the M7 pylon footing are 40 meters deep. Self-compacting concrete mix based on sulfate-resistant Portland cement was placed in the pylon grillage. The concrete will protect the footing against erosive fluids and prevent rebars from getting rusty. The highly flowable concrete mix was placed without interruptions for several days in 10 to 15 centimeter layers. Custom-made concrete pouring pipes were used to prevent unmixing. Strain gauges were installed in the pylon grillage to transmit data on concrete stress condition. Strain gauges ensure evaluation of structure condition both during erection and later in operation. The pylons are of a varying cross-section tapering upward. The bottom part of the pylons takes up the maximum load. For that reason, design provides for heavier reinforcement at the bottom part. High-grade concrete, which features substantially higher density compared to ordinary concretes, is placed to erect the pylon body. Custom-made self-climbing formwork is used to concrete the pylons in 4.5 meter high sections. A lifting crane lifted the formwork when the first 3 sections were concreted, and the formwork was then moved independently by hydraulically powered lift modules. The self-climbing formwork cuts down the cast-in-place reinforced concrete structure erection time by a factor of 1.5. The cable-stayed span structure is designed with an aerodynamic profile to take up a squally wind load. A scaled bridge model was tested in a wind tunnel. The navigation span stiffening girder is of an all-metal design. It is made as a box, making up the entire cross-section with the bottom orthotropic plate, the top orthotropic plate that supports the roadway, and with a system of cross beams and diaphragm. The still stiffening girder consists of 103 panels, each 12 meters or 24 meters long. The stiffening girder is 1,244 meters long. The panels weigh a total of 23,000 tons. The panels are pre-assembled at the production facility on the Nazima Peninsula and at Nakhodka shipyard. The panels are delivered to the installation site by barges and are then lifted by crane to the 76-meter elevation. The barge will be positioned under the installation unit using GLONASS, a Russian global navigation satellite system. The end spans are symmetrical with respect to the channel span and pylons. The continuous spans are made of pre-stressed reinforced concrete. Plastic ducts are installed in addition to rebars during reinforcement. High-tensile pre-stressing steel bundles are installed in the ducts. The steel bundles will be tensioned at 350 tons by pre-stressing jacks after concreting. Stay cable supports are installed in parallel with reinforcement work. The stay cable support is a low alloy steel pipe with an anchor base. The support diameter is 377 millimeters and is over 3 meters long, with a weight of about 1 ton. An improved stay cable system with a higher strand density within the jacket is used for the central span. Compact cable configuration using a smaller diameter jack reduces the wind load by 25 to 30%. This design cuts down the cost of materials for the pylon, stiffening girder, and footings by 35 to 40%. The cables are composed of parallel running strands, each about 16 millimeters in diameter. Each strand is composed of 7 galvanized steel wires. Stay cables consist of 13 to 79 strands. The shortest cable is more than 135 meters long, and the longest cable is about 580 meters long. The protective cable jacket is made of high-pressure polyethylene. High strength, durability, and corrosion resistance characteristics of the cables